What else? We can define kind of convenient combinators for programming. So we can define conditionals. We can define loops that go across lists and do something to each element. We can define while loops. I'm not going to belabor the details, but these trees give a nice kind of basis for building up programming notations. Okay. Let me show you some more interesting things about trees. Now let's get specific about what sorts of things these events could be. We've already hinted at a few things, so I've said socket operations and things like that, but we've also seen that we can have events that are like non-deterministic choices. And so let's see some more examples of that. So here, for example, is a type failure E. It's actually a type family, so it's a function from types to types. The type argument indicates the result type of each event. And so failure E is the event type corresponding to failures. It has one constructor, capital fail. It takes a string argument that describes the reason for the failure for debugging purposes. And that gives you back a failure E with result type void. That is, failure E, when plugged into an interaction tree, will give you an event node, a viz node with no children. And then we can wrap this fail with a capital F inside of a function fail with a lowercase f that returns an MEX for any type X. Which wraps it in the following way. So it constructs a viz node with a fail node inside it. And here's the tricky part. It uses this function convert, which changes the type of events from just failure E to any event type E that has a failure in it. And now that's something I have to explain. So we're going to want to deal with interaction trees over lots of different kinds of events. This fail function is an example of a generic combinator that says I can be used to produce trees where the event type is anything that includes a failure event. Now, what do I mean by an event type including something? Let's go up here. Events, or effects we sometimes call them, can be combined. We have a little algebra for combining effects where the plus tick operator takes two type operators, two sets of events is the way to think about it, and forms their union. And then the hyphen less than operator is a relation between a particular kind of specific set of events and a larger perhaps union of sets of events. So for example, E is pronounced convertible. So E is convertible to E. So if we're talking about trees that only have failure events, you can use the fail combinator to build trees of that form. Or E is convertible to F union E. Or E is convertible to E union F. In other words, this convertible thing is some type class magic, essentially, for looking inside of the actual set of events that you're talking about and finding a particular set of events that you want to talk about generically in some part of your program. I didn't say that very clearly. Let me try it again. We have operators like fail that don't care about what the whole set of events is. They only care that whatever the set of events is, it includes fail. So we want to write the actual set of events, the failure events are convertible to the actual set of events by embedding in one of these ways. Okay, so this just gives a little bit of genericity. Yeah, and so here's the type of fail. It says for any E that the failure event is convertible to, fail has type ME, and what is S?
S is Dutch.
Oh, S is anything, in fact. You can say it either way. It has any result type or it has void result type. It doesn't really matter. Okay, so that was failure. Here's non-determinism. So non-det E is again a set of events with just one event in it, as it happens, called OR. And then there's a lowercase OR, which takes two possible continuations, K1 and K2, which are both interaction trees over some set of events E, or requires that non-det be convertible to E. All right, so non-det, so whatever E is, it should include non-det, and OR squashes those two things together, putting a capital OR node at the root, and produces a single tree out of them. And then we could generalize that to an n-ary thing called choose, where E now should have both failure and non-determinism. Why does it need failure? Because if you give it an empty list, then it should fail. And if you give it a non-empty list, then it should give you a choice between all of the things in that list. And it's this that we use to implement the disjunction notation that we saw in the top level specification. Okay, questions?
So if your non-determinism were to decide to give false, 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 whatever, and eventually you reach the end of the list, then you run into failure. And so in that sense, if you were to actually execute it and plug in some non-determinism, like some actual non-deterministic oracle, you could possibly run into failure in that sense, even though you shouldn't really?
No.
Choose doesn't have a recursive call. That's the important part.
I'm not sure.
Choose calls choose prime.
Choose calls choose prime.
So does not have the fail case.
That is true, but I think that's not a helpful response because the question I think was based on a wrong intuition. So let me try to correct the intuition. So you might think that that choose is choosing between the list of choices that you give it. It isn't. All it's doing is building a tree with some OR nodes in it. How those OR nodes are interpreted, those OR nodes are just constructors. So how they're interpreted is a completely different matter, which we haven't talked about yet. I've been speaking as though there were a particular canonical interpretation, and in fact we are going to give a particular interpretation to OR a little bit later. But at the moment, we're really just defining syntax for building trees. And so now combining that intuition with Adam's answer, if you give an empty list here, you will get a tree with just a fail node. If you give a non-empty list, you will get, if you give a list with multiple things in it, you'll get a tree with some ORs at the beginning. But either way, the fail and the OR are just constructors that are sitting in the tree waiting to be interpreted later. Okay, in the interest of time, there are some more examples in this file of kinds of events that you can put in. For example, you can have state effects and the relevant event type has a get and a put constructor. You can have just the reader part of the state. You can have just the writer part of the state. So you can play lots of tricks with defining specific kinds of events. But I want to skip over that and talk about the specific kinds of events that I'm interested in for specifying and implementing network servers. Okay, so in this file, I'm going to show you just the interface. So notice that the top line there is module type. So the specifics of the implementation of all of this is elsewhere. I'm mostly just showing you the types of things, but I will show you a few specifics. So the first specific I'll show you is server E. So server E is the type of events that we use for implementing servers. So this is the type of events that would be relevant for building a reference implementation of a server. And there are three: accept, receive byte, and send byte. And accept, when accept returns a connection ID to its continuation. Receive byte returns a byte to its continuation. And send byte returns a unit to its continuation, but it's parameterized by, or it's annotated with the connection ID and the byte that are being sent. And now we can define a particular monad by applying M to these server events plus failure and non-determinism events. And so we'll use that. So server M will be the monad that we use for defining things like the C-like server that sits in the middle between the C program and the high level. And now, for convenience in programming these things, we can define some, so along with capital accept, there's lowercase accept, which is defined as embed of capital accept, where embed is just a little bit of type class trickery that says, take that constructor and wrap a viz around it and make it have the right type. Okay, so in programs, what you'll see is accept, receive byte, and send byte, but you should know that those are just thin wrappers around those three constructors for interaction trees. And now based on those, and using some of the combinators like while and for each and so on that we saw a little while ago, we can build some a little bit higher level operations like receive n bytes. Either up to n bytes or exactly n bytes, or send a byte string rather than just a single byte. Okay, so server E is the events for implementing servers. Observer E, which is here at the top, is the set of events for implementing specifications of servers. which we call observers. So observers, again, have three events. They can observe a connection happening. They can observe a byte going to the server. And they can observe a byte coming back from the server. These may look exactly the same as the events from before, but they're not quite the same. They don't have quite the same types. Up above, the receive operation returned a byte. The send operation was annotated with a byte that should be sent out. Here, both the observe byte being sent to the server and observe byte coming out of the server events return the byte. Why? Because we're going to use this to specify legal behaviors. So when we observe a byte coming out of the server, we don't say sorry, other way around. When we observe the outside world sending a byte to the server, so we observe the server receiving a byte, we're told what byte it received. When we observe the sender sending us a byte, we are also told what byte it sent us. Right? So the observer is not the one that's making, in particular for this, for observe obs2 server. The observer is not the one that's deciding what byte to send to the server. Somebody else is doing that, that's making up, that's generating the test case. The observe to server is just observing that the byte got sent to the server. Okay, one more subtlety is that when we observe bytes coming from the server, we don't always get the value that, that the byte has. We sometimes get none, which says, intuitively, the server sent out a byte, but the observer hasn't received it yet. So this is kind of a hypothetical operation that, that the specification is saying the server might have done that, but we haven't seen it yet. And this is useful in testing because in a testing context, you may be talking to a server over a network that's delaying some of your messages. And you want to have kind of a placeholder that says, I know there must be a message there because the specification says so, but I haven't received it yet, so I want to go on and see the rest of the messages in the communication and check whether they're okay. Okay, and then as before, we can wrap those constructors in lowercase, obs connect, obs to server, obs from server, and we can define some higher level operations that, that are built on those. Okay. One more thing, and then I'm going to show some concrete examples that, that should ground all of this. So we've been talking about these kind of infinite branching computation trees. These are not things that are easy to observe. What we actually observe are linear, finite traces of computations. Well, of the effects of those computations, of events happening on the network. So we need a way of talking about the traces that can be generated by, or the traces that can be accepted by one of these trees. And the way we do that is we define a type of events. Actually, to be specific, we define two types of events, depending on whether we're talking about kind of concrete traces or concrete events with concrete bytes in them, or more hypothetical ones that may have hypothetical